Hi everyone, my name is Latne. I'm recording for ICASSP2020. I hope you all are staying safe and healthy. I have a few slides prepared, so let's jump right in. The name of our paper is Overlap-Aware Diarization, Resegmentation Using Neural End-to-End Overlapped Speech Detection. Like I said, my name is Latne Bolik, and I'm presenting this work on behalf of Hervé and Lagni Paula Garcia Pereira. Hervé is a researcher at LIMSI in France, and Paula is an assistant research scientist at CLSP at Johns Hopkins. And I'm an undergrad at Rice University. We completed most of this work as part of the annual JSALT conference on human language technologies. The main focus of our team was diarization in adverse scenarios. Diarization is the who spoke when problem, which equates to assigning a series of speaker labels to time segments in an audio file. And by adverse, we mean a number of things. It could be adverse in turn, the audio file could be adverse in terms of the number of speakers in the audio. It could be adverse due to far field speech or noise. To give you an idea of the type of audio we're dealing with, I have an excerpt from Time 5, which is one of the corpora that we were dealing with.
I feel bad for people that need to watch this.
See, this is way more work to come.
No deal. No deal.
You're an and then mash the parts that aren't mashed.
Also,
as you can see, there's lots of background noise and overlap. And overlap is actually one of the main issues, one of the main challenges in tackling diarization in adverse scenarios. It leads to a high misdetection rate, which is one of the components of the overall diarization error rate, and often leads to a high speaker confusion rate. As you can see in AMI mixed headset, there is almost 19% of the time, there's more than one speaker speaking. In Chime 5, there's almost 34% of the time where two or more speakers are speaking. And the other corpus that we were interested in was Baby Train, and it had a little bit less, but I'm sure the ones that some of you are familiar with, AMI and Chime 5, clearly require handling overlap appropriately. The primary contributions that we outline in our paper are an overlap speech detection module and an overlap-aware resegmentation module, which takes advantage of the detected overlap speech regions and gives a final output for not only single speaker speech regions, but multi-speaker as well. The first step in our system is to detect the overlapping regions of speech. And we do so with Pianote Audio, which is an open source toolkit written in Python for speaker diarization. The problem is approached in 2-second audio chunks, which are passed to a recurrent neural network, which end up returning frame-wise scores and eventually a binary sequence of a binary vector, which encode the regions of overlap and non-overlapping speech with 1 and 0. We expound a little bit upon the network here with this architecture. The first few layers are either handcrafted MFCC features or SyncNet, which are then passed to convolutional layers, then onto long short-term memory layers, and finally a few feed-forward layers and a classification layer in the end to get the frame-wise scores and the overall hypothesis for the overlapping speech in the audio. As is often the question with machine learning, you may be wondering, so how is this actually trained? And there were a few issues that needed to be addressed, specifically with class imbalance, and that's because although overlapping speech does occur frequently, fairly frequently, it is not by any means equally frequent as non-overlapping speech, and so we trained with 50% of the samples coming from randomly randomly extracted audio from the original audio file in 2-second chunks, and the other 50% were the weighted sum of two different randomly selected audio chunks. And so those guaranteed that 50% of the, at least 50% of the training was on overlapping speech. And as you can see in this diagram to the right, we increased the number of positive training samples for overlapping speech detection by artificially creating them. At test time, we simply sum over frame-wise over the frames that are in 2-second chunks, and we end up thresholding, and we have a binary vector in the end with the regions of overlap and non-overlap speech. We report overlap detection results on AMI headset mix, DieHard2, and ITAP. We first note that the end-to-end variant, or the waveform row, consistently outperforms the handcrafted features, and so that's what we ended up using in the final model. We were able to set state-of-the-art performance on these three data sets. On AMI and ITAP, we were comparing to a baseline, and on DieHard, we were unable to find one, and so this sets the standard moving forward. We're to state-of-the-art performance on AMI and ITAP for overlap detection. Now, one of the main challenges is not only detecting those overlapping speech regions, but actually utilizing them in a useful manner. And so that's what we're moving on to now. This is what we call the overlap-aware resegmentation module, and we're going to use the results from the previous this previous module, the overlap speech detector, and incorporate them into this final resegmentation step to get a final output of who speaks when. We draw heavily on the work of Diaz et al. 2018, who propose a variational Bayes, hidden Markov model, Gaussian mixture model, resegmentation module. And so henceforth, I will call that the variational Bayes HMM GMM model. And we won't go into too much detail here because this was not the focus of our paper, but because we draw heavily on it, let's look at it a little bit. You have a hidden Markov model where each state represents a speaker, and the state distributions are Gaussian mixture models. And theoretically, this model should be able to perform inference with variational Bayes methods that gives you a final sequence of who spoke when in the audio. And so if you initialize this module, you only need just a few iterations will slightly decrease the diarization error rate. And so originally that's what we were using this VB-HMM resegmentation module for, but we ended up using it in a little bit of a different way for overlap-aware resegmentation. Most importantly, what we get out of the VB-HMM model is a speaker posterior matrix, which they call Q. And it's depicted here. You have from left to right voiced frames over time, and then you have on the top row the most likely speaker, and on the bottom row the least likely speaker. So in this example, there are 4 speakers in the audio, and let's say yellow is speaker A. Speaker A is most likely on for these first few frames, and then let's say green is speaker B. They're most likely here, and then back to speaker A. So this will end up being used in the overlap-aware resegmentation module, and this is a fairly straightforward methodology that we've implemented, but I will outline it here. So the top row of the Q matrix is here, with the most likely speaker, and it's masked with the voice activity detector, which these should line up perfectly because as you saw in the previous slide, these are only voiced frames. So we only have the Q matrix speaker posteriors for the voice frames. And so we mask it with the VAD, and we have a final, or we have a preliminary hypothesis as to the most likely speaker. And this is what's done traditionally in the VBHMM model. Our extension proposes to mask the second most likely speaker, which is the second row of that matrix, the Q matrix here. Mask this second row with the overlap detection that I described a few minutes ago. And so imagine you had overlapping regions in this area here. We would eliminate these second most likely voiced regions and just take these two speakers for a final hypothesis where you have speaker A speaking, speaker B speaking by themselves for a few frames, and then both speaker A and B in this final hypothesis. The results that we report are only on AMI headset mix, and the baseline that we started off with was a 29.6% diarization error rate, with yellow being confusion, red being the false alarm, and blue being the misdetection in the audio. So when we use overlap assignment, the overlap aware assignment in the resegmentation step, you actually get a pretty significant decrease of over 5%. And the trade-off is an increase in speaker confusion, which is easily understandable when you are making more hypotheses. You are naturally going to miss some of those. So this is the increase in speaker confusion. And the biggest decrease is in the misdetection. We also performed a couple of experiments where we had oracle overlapping speech detection and then performed the overlap assignment. And you see that there's still significant error when you had oracle detection. However, when we did the converse, when we had oracle overlap assignment, oracle overlap assignment from the automatically detected overlapping speech, we saw almost 50 or 100% decrease, I guess, 50% decrease from the overlapping assignment to the oracle assignment, which shows us that most of the future improvements will come from the overlap assignment step as opposed to the overlap detection step. The overall conclusions and takeaways are that we were able to detect overlapping speech on AMI and ATOP with state-of-the-art performance, and then we set the standard for Die-Hard 2. The primary gains in the future for a methodology like this will come from better overlap assignment, and we view this as a first step, a good step in the right direction, but certainly not as an end-all solution. If you have any questions about reproducibility or using the code, please reach out to us. Our emails should be on the paper, and we'd like to acknowledge JSALT, the L'École de Technologie Supérieure, which was the location of JSALT last year, and finally Johns Hopkins, as well as Amazon, Facebook, and Google, and Microsoft, who supported JSALT last year. And thanks, ICASSP. I hope all of you stay safe and enjoy the conference.